Alright, what's up guys? This is a review video for your final exam review. Specifically, this is the second test over logs and exponential functions. Alright, before we start on the questions, I want to talk about these four equations up top. So these are the equations. We'll really just use these on the back of this sheet, but I want to make sure we talk about which one is which. The first two, when we talk about exponential growth and decay, remember these were not given to you when we originally took the test. Okay, the big difference is the plus and the minus sign between the 1 and the r. And it makes sense that when you add your 1 plus your rate, you're going to do exponential growth when things are increasing, and then when you subtract, it's going to be exponential decay where things are decreasing. Okay, so these first two equations are exponential growth and decay. These last two are the ones you were given. They kind of have keywords that tell you when to use them. And the first one is what we call PERT. Okay, it's when we talk about compounding continuously. So anytime you see compounding continuously, we're looking at PERT. This last one is when we compound either monthly, so monthly could be a word you'll see, or quarterly. Those are the two most common. You could also have something like weekly, sometimes daily, whatever, but monthly and quarterly are your most common times you see that. So we'll use those on the back, but I just want to see those from the start right here. All right, jumping in to question number 1. How would you write 4 to the negative second power is equal to 1 over 16 in logarithmic form? All right, depending on your teacher, this could be shown to you in a couple of different ways. Some of you probably learned to take the log base 4 of both sides. So if I take the log base 4 of this side, that means I need to take the log base 4 of this side. Alright, when you take the log base 4 of 4 to the negative 2, remember those kind of pair up and go away. So you're just left with negative 2 on the left side, and on the right side you have log base 4 of 1 over 16. Alright, you might have learned to convert. That's kind of how I teach it. When you convert, you just take your base and you drop your base. So you're going to convert this exponential to a log. So I'm going to start with a log. I'm going to drop my base to be 4. I'm going to kick my exponent out to be negative 2, and I'm going to slide this 1/16 in. Alright, either way you get the same answer. This is going to be answer choice B. Log base 4 of 1 over 16 is equal to negative 2. Alright, when you get to number 2, same process, just kind of in reverse. Alright, so how would you write log base 3 of x is equal to r? Alright, if you convert, I'll do this one first. We're going to raise our base, and we're going to bring our exponent in and slide out the x. This is kind of what I call converting. So 3 to the r is equal to x. Okay, you also might have learned to raise both sides to the third, or to raise both sides to a base of 3. So you could do 3 log base 3 of x is equal to 3r. Alright, 3 and the log base 3 go away, so you just end up with x is equal to 3 to the r, which is the same thing I got here as well. So your answer here is going to be D. Alright, those are those first two, just simple conversions. Make sure you know those, though. They're too simple to miss. Alright, number 3. So when I write out number 3, this is where we have to talk about our expansion rules. Alright, so remember, we want to write a log for each of these different variables, x, y, and z. The 3 rules we talk about deal with exponents. Remember, we're going to move exponents to the front of the log. Okay, they deal with kind of things on top and bottom, right, or things being multiplied. When things are on the top, they're going to be added. And when things are on the bottom, they're going to be subtracted. Alright, so let's just start with the first. So I'm going to have a log of x. And remember, I moved that exponent of 2 to the front. So 2 log of x. Alright, and then everything from here on out is on the bottom. So I'm going to subtract everything from here. So the next one is going to be a subtraction of log y. No exponent for y, so I'm good. And then a minus 5, which is my exponent. Don't want to miss that. 5 log z. Alright, so b and d can be eliminated because they don't follow the exponent rule. When you get over to a and c, A has the two subtractions, so that's going to be the answer here. Okay, number 4, solving with these logs. Couple different things to show you here. First one in A, and you have logs that are the same on both sides. So there's just one log on each side of the equal sign, and they're both log base 3. Essentially, you can just get rid of these. So that means I just have x plus 4 is equal to 2x minus 6. I can subtract my x over. 4 is equal to x minus 6, add that 6, and x is equal to 10. All right, remember the only check we really have to make is we have to plug that 10 back in to make sure we don't get a negative log. So plug it back to your original, anywhere you see the log with an x in it, and make sure it doesn't become negative. So I plug in 10 here, 10 plus 4 is 14, that's positive, so I'm good. Plug in 10 here, 2 times 10 is 20, minus 6 is also 14, which makes sense, and it's positive, so I'm good. So my answer for letter A is just x equals 10. All right, for letter B, notice there's a difference here. There's only one log. Okay, so when you get to this point, you have to either convert like we did in 1 and 2, or raise both of these sides up with a base of 2. All right, I'm going to do converting. It's the same stuff we did in number 1 and number 2. You should kind of understand that by now. But when I convert, I raise the base and bring in 3 to be my exponent. So I'm going to have 2 to the third. And I'm going to kick out that 4x minus 8. All right, that's my conversion here. It's from log to exponential form. If you raise them, if you raise both sides as a power with a base of 2, you're going to get the same result. All right, now to solve, 2 cubed is 8. It's equal to 4x minus 8. All right, I'm going to add this 8 over. So I get 16 is equal to 4x divided by 4. X is equal to 4. Plug back in to make sure it stays positive. 4 times 4 is 16. Minus 8 leaves me with a positive 8. So I'm good with that. And x is equal to 4 there. All right, letter C. So notice the difference in like C and A. So we have multiple logs. A, they're the same log, one on each side. C, you have all the same log, but there's 2 that are being added together on the left side of the equal sign. This is where we have to follow our condensing rules, which means we take things that are being added and we write them as one log of base 2 in this case being multiplied. Remember, addition means multiplication. So 3 times 2x plus 4. Right side goes unchanged. Log base 2 of 36. All right, I'm going to go ahead and distribute here. So log base 2 of 6x plus 12 is equal to log base 2 of 36. And now we're at the same point we were at with A. I can get rid of these log base 2's. 6x plus 12 is equal to 36. And I can solve here. 6x is equal to 24. X is equal to 4. Alright, make sure it doesn't give you a negative. The only place to plug it in is right here. 2 times 4 is 8. 8 plus 4 is 12. So it's positive, so I'm good. Alright, letter D. Have the natural log on both sides. Remember, natural log is just log base E. So it's the same thing. Alright, kind of goes back to A here. I can kind of get rid of these natural logs. So I just get 6x plus 21 is equal to 2x minus 3. Alright, I want to subtract this 21. 6x is equal to 2x minus 24. Subtract the 2x. And then divide by my 4 here. And I end up getting x is equal to negative 6. Alright, when I plug this back in, let's just plug it into the right side. I get negative 6 times 2, which is negative 12. Negative 12 and negative 3 makes negative 15. So when I plug this back in, I get the ln, or natural log, of negative 15. That is not okay. Not allowed to have a negative log or natural log. So that means this is not my answer, not a valuable or not a feasible solution. So this is going to be no solution. Okay, moving on to the back. This is where these equations will come into play that we went over at the beginning of the video. All right, number 5, Lucy deposited $2,800 to an account that earns 3.2% interest, compounded continuously. There's our keyword, continuously. After how many years will their account exceed $30,000? All right, on the front we said continuously. We're going to use PERT. So for this PERT, tell me that A is equal to P times E to the RT power. All right, let's label what we know. So the $2,800 that she initially starts with is our principal, or our starting amount. So that's going to be P. All right, 3.2% interest, that's our rate. Remember, we always want to convert that to a decimal, so 0.32. All right, down here we get our A, our ending value. So we know we want to figure out when she has $30,000, which means we need to find our T, or how many years it's going to take her to get there. All right, I can plug these in. So I get 30,000 is equal to 2,800 E to the R, which is 0.032 T. Remember, E is not a variable. E is what we call Euler's number. Kind of goes directly with natural log. We don't want to plug anything for E. It stands for 2.71, though. That's its value. It's kind of like pi. All right, knowing that, we don't want to multiply here. All right, we want to go ahead and divide this 2,800 over to get our exponent by itself. All right, our exponential go by itself. So we divide that. When you do 30,000 divided by 2,800, that gives you about 10.71. All right, so I can say, I'll move back up here, 10.71 is equal to E to the 0.032 T. All right, and this is a situation where we would convert. All right, so I'm going to drop my base to get log base E, which is just ln. So I'm going to get ln, which is log base E. I'm going to kick my exponent out. So I'm going to get 0.032 T out here by itself, which makes sense. That's how we get T out of that exponent to solve for it. And now I'm going to get 10.71 in here. All right, now to solve, we just got to get T by itself. So we're going to divide by 0.032. So I end up with T is equal to the natural log of 10.71 divided by 0.032. I could plug that in on my calculator directly. All right, 10.71. ln of 10.71 gives you something like 2.37, and then just divide that by 0.032, and we end up getting 70 or 74.99. So we'll round that up to 74.1. So T is equal to 74.1. Remember, that represents the years. That's how long it's going to take her to have $30,000 in her account. All right, moving on. Letter B. If she waits for 40 years, how much will her account, or how much money will be in her account? All right, we're really switching a couple things up here. We're not switching how much she starts with. We're not switching the rate, or that it compounds continuously. So we're still going to use PERT. Okay, the difference here is they tell us how long she's going to leave it, 40 years. That's our T. And now we just want to find A, her ending amount, how much will be in her account. All right, so for this, I'm going to say A is equal to 2,800 E to the 0.032 times 40. Okay, so now this is just where I can just plug everything in together, and I can get a pretty easy answer out of this. So 2,800 E, that comes from the second natural log on your calculator. You're going to do 0.032 times 40, close that parentheses out. And after those 40 years, she's going to have about $10,070.59. All right, so notice how it kind of changes depending on what we're finding. All right, but it's helpful to know what you're finding, because that kind of will tell you obviously what you plug in for and kind of how you go about solving for that variable. Okay, number 6, you deposit $1,600 into a bank account in 2015. The account pays 2.4% annual interest compounded monthly. There we go, keyword. Find the balance of the account in 2018. Okay, this is our compounding interest equation. So A is equal to P times 1 plus R over N to the NT. This is the same exact equation you see right here. Okay, so now I've got to just label what I know so I can plug in and figure out how much she's going to have in the end. Alright, so I know my principal. What I'm starting with is $1,600. And then my rate is at 2.4%, which is 0.24 as a decimal. Okay, I know I'm compounding monthly, so that means the N is going to be 12 months. And my time is going to come from subtracting these years. So to get time, I'm going to do 2018, this is a simple one, minus 2015, which leaves me with 3 years, right? So her T is 3. Okay, now I can plug everything in. So I want to find my ending value, find my ending balance. So finding A, I can say 1,600 times 1 plus R, 0.024 over 12, which is my N, times 12 to the T, which is 3. Alright, you can plug all this in on your calculator at once as long as you pay attention to parentheses. So I can say 1,600 parentheses 1 plus, this is where you got to insert another one. So when you plug it in, you want to insert parentheses around that fraction. So 0.024 divided by 12. Close it out twice. And then raise it up to an exponent, which is this little up arrow. Start a new parentheses, 12 times 3. She's going to have, or you're going to have, $1,719.32. There we go. Alright, part B, we change one thing. So we only change it to quarterly. So our big difference here, everything else is going to stay the same, but my N value is going to change from monthly of 12 to quarterly, which is 4. So I'm going to go ahead and I'm going to plug in the same exact stuff that I know from above. Start with $1,600, 1 plus, same rate, 0.024. I'm going to change the 12 to 4 here though. And then my exponent is also going to change to 4 times 3. Alright, 3 being the years. So I can plug this in, same way I just plugged the last one. 1,600 plus, make sure you put that parentheses before the fraction. And then put your exponent in parentheses, 4 times 3, which you know is 12. Alright, in this case, with just a little change here, she's going to have slightly less money, not by much. Still going to have that $1,719, but now she's only going to have 8 cents, rounded up. Alright, so slight difference. 3 years is not that much time, so that kind of makes sense. Alright, and the difference in monthly and quarterly isn't huge, but there will be a slight difference here. Okay, moving on. Number 7. You have inherited land that was purchased for $30,000 in 1960. The value of the land increased, so that's important. It increased by 5% a year per year. What is the approximate value of the land in 2011? All right, so I have an increasing situation. So this is going to be exponential growth. So the first equation we talked about on the front. So my exponential growth equation is this right here. A of t is equal to A times 1 plus R to the t power. So I'm going to say A of t, which is my ending value, is my starting value A times 1 plus R to the t power. Okay, so I know that A, my starting value, which is also kind of like P up here, is this $30,000 that the land was originally bought for. Okay, my rate is 5% per year, so 0.05. And then my time, this is where I'm going to have to really make sure you understand to subtract. So I'm starting in 1960 and ending in 2011. All right, so if I subtract 2011 minus this 1960, you can go through and do all the math here, but it's going to end up giving you 51 years. All right, like I said, if you just do it on your calculator, that works too. Or do it by hand, doesn't matter, 51 years. All right, so my t is 51. I want to find my a of t. Okay, so in this case, a of t, really, a of t is a of 51, because that's our value for t, is equal to 30,000 times 1 plus 0.05 to the 51st power. Alright, you can plug that in. 30,000 parentheses 1 plus 0.05, close your parentheses and raise it to the 51st power. That land is going to be worth a lot of money. After those 51 years, it will be worth something like $361,223, $223,009. Alright, so that's your final value. Increased a lot over those 51 years. Okay, last one. Drew bought a car 5 years ago for 10 grand. The value decreases by 10% each year. How much is the car worth now? Alright, very similar up here. Only going to change the fact that because I'm decreasing, I have decay, which means I'm going to subtract on the inside of my parentheses. Alright, so his starting car value was $10,000. It was 5 years ago. Alright, so that'll be our t. And our rate is this 10% decrease per year. So 0.1. So when I plug this in, so that a of 5 is equal to initial 10,000 times 1 minus 0.1 to the t power. Plug that in. 10,000 times 1 minus 0.1 to the 5th power, and I get a value of about $5,900. So we'll say $5,904.90. Alright guys, that's the second section from test number 2.